Good morning, everybody. Thank you, Patrick. Thank you, Brandon, Kimberly, Ernesto. Thank you, everybody. Ronald, Matthew, Emily. Okay, all right. Well, talking about complex numbers and complex analysis. Uh, so before going to the lecture, I want to inform you that your TA contacted me a little late, of course, after I gave you the handouts. So contacted me. The name is Abraham Kuznia. Abraham Kuznia is a TA. It's a graduate student, and he's here to work with you on Fridays and help you, and hopefully, I'm sure he will be very helpful to a lot of you. So now back to complex analysis. Let me get to my whiteboard. All right. So we talked about the set of complex numbers that generalizes the real numbers. And for us, that set of complex numbers denoted by this is the set of, let's say, x plus I, y, where x and y are real numbers, all right? Okay. So I talked about the arithmetics of complex numbers. We talked about addition, subtraction, multiplication, and also division, right? Now, in the process of, especially later, of course, in the process of division, I introduced a conjugate. So if you have z equal x plus iy, conjugate of z is denoted by z bar and is x plus iy. Okay. Well, anytime we introduce a concept, we really would like to find the properties. What can we do with that concept? With the properties of conjugation, here is the properties. I am just reviewing for just in case if some of you missed the class on Tuesday. Properties of conjugation, okay? The first one is if you have two complex numbers and you want to take conjugate, it is this one plus this. So conjugate of sum is sum of conjugates. Okay, let's put it this way. The same is true for the difference, all right? And interesting enough, the same is true for multiplication. If you have two complex numbers you want to get a conjugate, it will be conjugate of the first one times conjugate of second one. This one, we can expand it, we can generalize it. Instead of two, you can have three, four, all right? In general, okay, let's put it this way then. if you have z1 multiplied by z2 multiplied by zn, and you want to take conjugate, it's the same as conjugate of z1 times conjugate of z2, all right, and so forth. Especially this becomes very interesting when all these z1 to zn are equal. So if they are equal, on the left-hand side, you will have z multiplied by itself n times, which will give, usually we denote it by this, all right? Z multiplied by itself n times. And conjugate of this, the right-hand side will be conjugate of z multiplied by itself n times. So in a way, you can interchange these two operations. Operation of conjugation and operation of exponential, they are sort of can be commutative. You can interchange them. Anyways, another property is about the division of two. If you want to divide, and whatever the result, then take conjugate. It's the same as conjugate of numerator divided by conjugate of denominator, right? Good. After this one, we talked about geometric representation of complex numbers. And I sort of give you three different perspective. You can think about a complex number z equal a plus bi as a point, all right, as a point in plane. Or you can think about this as a vector, a plus bi, as a vector with components a and b. And then you can, of course, when you represent this or think about it as a point in the plane, every point can have also the polar representation. Here is the point z. Here is a and b, all right? So instead of ordered pair AB, we can say we can represent this in a polar format. Theta is this angle made by positive direction of x-axis. And the distance from this point to here, okay, the distance. And that distance is what we call modulus. This is square root of a squared plus b squared. And theta is, we call it argument. So we definitely know that tangent of theta is b over a, okay? That is modulus. This is argument. And whenever theta is between negative pi and pi, we will call it principal argument. Okay. Well, this taking modulus of z, this is a new concept, right? Like that conjugation, this is a new concept. You have a complex number. And what is modulus of that complex number is right here, okay? What are the properties of modulus? Okay, let me talk about properties of modulus. So here come properties of modulus. Well, the first thing is about multiplication. If you have two complex numbers multiplied by each other, modulus of this one is product of the moduli. That's very interesting one, okay? And very useful one, by the way. I'm going to give you a bunch of application for this one. But as before, we can generalize this one. Well, in mathematics, whenever you introduce a concept for two mathematical creatures, you can generalize it for several of them. For example, here, instead of 2, I can have 3 or 4, in general, n of them. So you multiply this and take the modulus is the same as taking modulus of each one and then multiplying by each other. Okay. And again, as before, this becomes very interesting when Z1 through Zn's are equal. All of them are Z, let's say. So the left-hand side will be modulus of Zn. The right-hand side, modulus of Z will be multiplied by itself n times. So will be this to the n. Again, these two operations can be interchanged, okay? These two can be interchanged. Okay, this is a very good one. Please pay attention to this one. So property number 1 is this one that can be generalized this way. Here is property number 2. For division, when you have Z divided by W, you can do the division and then the result is a complex number, take its modulus. This is the same as modulus of Z divided by modulus of W. How about that? Isn't that nice? Okay. It is easy to verify this thing, all right? Those of you who are really interested in the proofs, you can easily verify. And if you have any difficulty verifying it or accepting it or cannot really prove it, just let me know next time. I will be glad to help you on that one, all right? Okay. But the application of these two, here is the application of 1 and 2. I want to find the modulus of something very, let's say, strange, very strange. You're going to have a question in your test number 1, like this, like this example that I'm going to give you. So you will be asked, find modulus of this fraction. For plus 3i to the 10, 1 minus I to the 4th divided by 1 plus 2i to the 18. Well, think about it. If we want to do the arithmetic here, raised to the 10, raised to the 18, and then divide, and at the end find the modulus of that complex number, that is going to be a lot difficult and challenging, a lot of work. But I am going to use these properties. Property number 2 says, if you want to find the modulus, it is the same as modulus of numerator divided by modulus of denominator. So we start with that. So here, this is what I am after. Divided by, okay. Oh, look, this is equal to, based on property number 2, modulus of denominator and here modulus of numerator. Okay. Now I'm going to use property number 1. And remember, property number 1 is about multiplication. And we generalized it, and we came up with this. Well, so it is about multiplication. So these two are multiplied by each other. It will be modulus of this one times modulus of that one. Good. So next line, I'll have in denominator 1 plus 2i. In numerator, okay, modulus of this one. Well, that's good. That's good. Now, again, going to that property number 2, number 1. Remember, in property number 1, when we generalized it, you can switch the modulus and exponential operations. So that means in here, I can say, instead of saying modulus of this guy, I can bring 10 out. So it is modulus of 4 plus 3i to the 10 times modulus of 1 minus I to the 4th. Here, modulus of 1 plus 2i to the 18. Okay. Well, you see how simple it is now, because I can just go ahead and find modulus of 4 plus 3i. And what is modulus of 4 plus 3i? It's right here. 4 plus 3i is the square root of this is square plus this is square, which is 5. How about 1 plus minus I here? 1 minus I modulus is square root of this is square plus negative 1 square. So it is the square root of 2. Finally, for denominator, what is modulus of 1 plus 2i? It's the square root of 1. This is square root of 5. Now, putting these in here, so the answer would become, this is 5. Okay. 5 to the 10. This is square root of 2 to the 4, which will give us 4. In denominator, it's a square root of 5 to 18. Oh, that's a square 5 to the 9 and canceled. So it's 20. The answer is 20. Okay. So you see, those properties make life a lot easier. So in your test, if I ask you to find modulus of such a thing, this very, very obnoxious fraction, you know how to do it. Any questions so far? Okay, yeah, there is a question here from Emily Garcia. Okay, are you there, Emily? Okay, are you the one that took Calculus 3 with me a couple of years ago? Oh, yeah, I remember you. Okay, so the homework, the handout that I gave you at that time, I didn't know you are going to have a TA. Now that we have a TA, I'm going to make TA responsible for the homeworks. Okay. Now, tomorrow when you meet Abraham Kuznia, he will tell you what to do. I am going to make him responsible for your homeworks and homework grades. Okay. All right. Hopefully, he will tell you what to do tomorrow. Okay. So I noticed that some of you send me your homeworks that uh, doesn't count, and especially that please don't send me until I ask for it. So usually you come to the class now that you go to, on Friday classes, and Abraham will tell you whether to turn in your homeworks or not. Okay. All right, Emily. Okay. Now, uh, going back to properties of modulus. Remember, modulus is just the distance from the origin to the uh, point. However, when it comes to this one, you have z1 plus z2. For multiplication, we notice what happened. But here, you cannot, oh, let me emphasize, you cannot say this is equal to modulus of this plus modulus. So no, no way, no way. This is less than or equal to z1 plus z2. This is called triangle inequality. Triangle inequality, all right? And we call it triangle inequality, especially if you think about it as vectors. Here is, let's say, z1, and here is z2. Think about it as a vector. The z1 plus z2 will be this diagonal, right? This diagonal. This is z1 plus z2. It's like vectors. So you look at this triangle. Modulus of z1 means the size of, I call this one z1. All right, let's call it z1. Here's z2. So modulus of z1 means this length or this length. Modulus of z2 means this side. Sorry, this one. So this is modulus of z2. And this is z1 plus z2, right? When you have two vectors, you add them, you get this. So the length here is z1 plus z2. So the reason why we call this triangle inequality, because in each triangle, each side is less than or equal to some of the other two sides, right? Each side, especially this, is less than or equal this side plus that side. That's called triangle inequality. I will call it triangle equality number one, because on the other hand, this you can even have a negative sign here. That's perfectly fine. And triangle number two is this one, that C1 plus C2 is bigger than or equal to the difference between these two lengths, Z1 minus Z2. So again, you can have a negative sign here as well, all right? You can have negative sign as well. The reason why you can have negative sign is that always modulus of Z is the same as modulus of negative Z. Oh, that's a good property. Okay, so triangle inequality number one, triangle inequality number two. They are useful when you want to find an upper bound for a rational function, and I will talk about that in the near future. Okay. All right. Now comes the polar representation. I told you that if you look at this complex number as a point, you will have here, you will have theta, and this is R. This is A, and of course, here is B. Well, just using this triangle, you know that cosine of theta is adjacent divided by R, the hypotenuse. So A is R cosine of theta, and B is R sine theta. What is R? Oh, here, R is the same as modulus of Z. Putting this together, you will get the polar representation of the complex number. Instead of A plus BI, which is an ordered pair, okay, you can say let's factor R, which is modulus of Z. Then you have cosine theta plus I sine theta. And then I talked about Euler's formula. Here is Euler's identity or formula, or whatever you want to call it. This can be easily established. So e to the I theta or Ix or whatever, I something, okay? I theta is cosine theta plus I sine theta. So if I use this Euler's identity right there, this is what I get. Z is modulus of Z e to the I theta. There are some very useful application for this one. Last time I talked about one of them, all right? So application of just this Euler's identity. One of them is called the de Moivre formula. So here is de Moivre formula. Which you raise it to the nth power. you get cosine of theta plus I sine theta to the n, and equals e to the I n theta. And e to the I theta is cosine of n theta plus I sine of n theta. That's application number 1 for Euler's formula. Okay. Now, here is application number 2. In application number 2, we want to find the a complex number raised to some very weird power. Here, let's say to compute, all right, z to the n, z to the n. It will be easy if we can write z in terms of exponential format. If we have it in terms of r e to the I theta to the n, this will be r to the n e to the I n theta. Okay? So to compute z to the n, it will be very advantageous if we can write z in its exponential format, same as polar format. Now let me give you an example here. How about I want to see what happens to, let's say, 1 minus the square root of 3i to 15. This is a good example for this application number 2. Well, I strongly recommend that whenever you want to write a complex number, in this case 1 minus square root of 3i, in polar format, just go ahead and plot the point. Here is 1. Here's the square root of 3. Negative square root of 3. So this is the point, 1 minus the square root of 3. So the argument here that theta is this one. So the usual principal argument, if you find one argument that's good enough in this, I mean, whenever you want to raise to some power, one argument is enough. What about the modulus? Well, modulus of 1 minus square root of 3 is the square root of 1, square root of squaring this is 2. How about theta? Look, theta is here. Theta is negative pi over 3. All right. So this 1 minus the square root of 3i, I can write it as 2 e to the negative pi over 3i. now go ahead and raise it to the 15th. This is what we want, right? This is what we want to the 15th. So 1 minus the square root of 3i to 15 is 2 to the 15 e to the negative of this to the 15, you multiply. So 15 pi over 3i, which is, by the way, 2 to the 15 e to the negative 5 pi I. So you might ask, what about this now? Well, it's not that bad because then you have Euler's formula. Remember Euler? Euler's formula is very, very beautiful and necessary for us. So Euler identity, it says e to the I theta is cosine theta plus I sine theta. So what is e to the I pi? We're using theta equal pi, e to the I pi. You know, sine of pi is 0, cosine of pi is -1. How about that? What is e to the 2 pi I? Well, you know, again, sine of 2 pi is 0, cosine of 2 pi is 1. Well, in fact, whenever you have multiple of 2 pi, e to the 2k pi I is 1. All right? K can be negative or positive, doesn't matter, right? Because cosine of negative theta is the same as cosine theta. So here, going back to this, you can write e to the negative pi, 5 pi I, negative 4 pi I, or I can even write it negative 6 plus pi I. But e to the negative 6, which is multiple of 2, it will be 1 e to the pi I, and e to the pi I is negative 1. So the answer is negative. So what is the result? The result is this: 1 minus the square root of 3i to the 15, which was 2 to the 15 e to the negative 5 pi I, is actually negative 2 to the 15 done. It's that is power, that complex number raised to power 15. Any comment, any questions so far? No question? Good. All right, thank you, Patrick. So this was The second application for that Euler's formula or polar representation. Here is the next one. And that next one is very interesting. Another application is when you want to take the nth root of a complex number. Nth root of a complex number. If we can write this, if you can write z as its polar format, which is modulus of z e to the I theta. But remember, since e to the any multiple of 2 pi is 1. So I am going to write this z as modulus of z, then e to the I theta plus 2k pi I. Because e to the 2k pi I is 1. It is just like multiplication by 1, right? Now you go ahead and take the nth root. Nth root of z is nth root of this number and nth root of this number. Nth root of this one means just this e to the I theta plus 2k pi I. Right? How about k? What is k? K goes from, we can say 0, then 1, 2, up to n minus 1. If you go n, you get 2 pi I, e to the pi I is 1. You will get back to this one. So the nth root of a complex number, you have n different answers, right? N different answers. Well, here is an example. But before giving you the example, I can sort of modify this and say, look, this is nth root of z, modulus of z, e to the I theta to the over n times, this part is fixed. This part, 2k pi I divided by n. And k goes from 0 to n minus 1, all right? So these are actually, if you just consider these by themselves, these are the nth root of 1. So this part, just this part, I am just going to justify why this will produce nth roots of 1. Usually we call unity, but 1. No. What do I mean by this? if you want to solve this equation for z to the n equal 1, well, depending on whether n is even or odd in real number system, you get either one answer or two answers, right, for real numbers. For example, when you want to do x to the 10 equal 1, you only get x equal plus minus 1. That's it. The remaining will be complex numbers, right? So this equation in calculus has only two solutions. And this equation has only one solution. But when it comes to complex, this equation has n different solutions. N different solutions. Okay, I'm going to find those n different solutions because in this case, if you want to solve this equation, you write 1 in polar format, right? Okay, here's how we write 1 in polar format. This is 1 right there. So the modulus is 1, theta is 0. But don't forget about 2k pi I, that's it. So 1 is e to the 2k pi I. So putting this together, in fact, I want to solve this equation. Okay. And that equation, you take nth root, you will get z equals e to the 2k pi I divided by n. And you will get n different solutions depending on k, of course. K goes from 0, which will give you 1, then 1, 2, and so forth, up to n minus 1. If you let k be n, you will get back to this. I'll give you an example. Yeah, why not? Let's have an example. How about doing z to the 4 equal 1? Well, this is easy, of course, but why not? Let's do it. So you say this is e to the 2k pi I. As a result, the fourth root of 1, okay? Take fourth root. So the fourth root of 1 will be, e to the 2k pi I divided by 4. What about k? K goes 0, 1, 2, and 3. Okay. So the fourth root of 1, in other words, the solution to this equation z to the 4 equal 1, or when k is 0 is 1, so with k equals 0, you get 1. with k equal 2, you get 4 pi I, e to the pi I is -1. With k equal 3. Oh, did I? Oh, I forgot 1. Okay. Well, k equal 1. You get e to the pi I over 2, e to the pi over 2 if you go ahead, and you will get I. So k equal 3 will give you, anyways, will give you -1, and the rest, oh, this is 2, will give you -1, and k equal 3 will give you -I. So this equation z to the 4 equal 1 has these 4 solutions, plus minus 1, plus minus I, right? So this is a very interesting phenomena. In real number systems, you might have an equation that doesn't have any solution at all. But in complex analysis, if you have a polynomial of degree n, then you are sure that you are going to have n different solutions, all right? Okay. Any comment, any question? Well, I sort of gave you a quick review of section 1 and 2, but unfortunately, yeah, I wouldn't have enough time to talk about section 3. So why don't you study, read your section 10.1, 10.2, okay, and 13.1, 13.2. So here is, yeah. Go ahead and read 13.1, 13.2. Do all the problems. Now you can do all the problems of those 2 sections. De Moivre formula, sure. Christian is asking, going back to De Moivre. We will go there. But for the time being, make sure that you, oh, here's what, by the way, here's what I recommend to my students. If you take notes in the class, that's perfectly fine. After the class, you go through your notes and just refresh your memory that what was done in the classroom. But that's not enough. After reviewing your notes, now go back to your text and read the text, okay? Oh, please, in all your courses, not just in my course, read the text and then especially pay attention to the examples that are done in the textbook, and then go and solve the exercises or the problems that are assigned to you. All right, so let's see. Christian, You want me to go back to De Moivre formula. Let's see, where was it? Okay, here it is. This last line. All right. Any comment about this De Moivre formula, Christine? Or you just wanted to write it down? Well, you're welcome. All right. Any other comment or question? That is fine. That is fine. I'm glad you did. All right. If there is no question, then take care. Uh, go tomorrow to your practice session, and I will see you on next Tuesday.